Thank you for the introduction and thank you for the invitation. It's a pleasure to give a talk in this seminar. And so I'll talk primarily about homogenization in front propagation models. And then when I talk about the proofs, then there will be a couple of new elements, and one of those will be non-autonomous subadditive theorems that I'll mention. So the basic model I've been interested in for a long time is the reaction-diffusion equation, which models various physical processes such as combustion, chemical kinetics, population dynamics, and others. And so in it, U is either a temperature or concentration or density, depending what it's modeling. And then we have a diffusion operator, which frequently is the Laplacian. And then we have a reaction function, which may depend only on U or may also depend on time and space. And so this reaction, may be birth and death process in population dynamics, may be due to some kind of burning, so increase of temperature due to burning and combustion, etc. Of course, chemical reaction due to molecules reacting. And so that's the basic model, and we can generalize it by replacing the Laplacian diffusion, which is homogeneous and isotropic and all that, time independent. We can replace it by a general space-time dependent diffusion operator, second order. And so then it also can include advection. So then we can call it the reaction-advection-diffusion equation. And so the U is initially given at time 0. And we want everything to stay normalized. So the reaction will be such that, so this is frequently assumed, such that at U equals 0 and U equals 1, it vanishes. And therefore, if the initial condition is between 0 and 1, easily by comparison principle, you can see that the solution also stays between 0 and 1. And then we, of course, think of U as a normalized temperature or concentration, etc. And we are frequently looking at a situation when values U and 1 are equilibria, and we are asking about the dynamic between these two equilibria. So either one of them may be unstable and the other one may be stable, and then we are transitioning from the unstable to the stable, or maybe even both are stable, but one of them is more stable, at least from a global point of view. And then we are again looking at transition from the less stable to the more stable one. Okay, so in this talk, we will have U equals 0 to be unstable equilibrium and U equals 1 to be stable. And so the equilibrium 1 will invade the region where initially we have value close to 0. And so you can think of some kind of biological invasion or some kind of forest fire, which is initially localized. So the solution is initially close to 1 in a, say, bounded region, and then it's close to 0 in the rest of the domain. And then this boundary region is going to spread into the whole space, which is a, let's say, d-dimensional space. Okay, and so the goal here is, of course, to find out something about this transition or this spreading of the region of the, let's say, the burning region. And specifically in a situation when we have a random environment, because in that case, one might hope that this randomness sort of averages over large space and large time. And if we are looking at the process, therefore, on a large space-time scale, we could see some kind of effectively homogeneous behavior. And this is called homogenization. Okay, and so one could hope for it in a situation when the environment is periodic in space and time, or even when it's random with reasonable order, so something like stationary or ergodic. Okay, so this is called homogenization, and so this is the goal of my talk and work in this area. And so what kind of reactions we'll be talking about? So that's the main ingredient here. And so I'll talk about so-called KPP reactions, which are named after Kolmogorov, Petrovsky, and Piskunov. And so these are reactions which have the property, so this is the reaction as a function of U for some fixed T and X. Of course, it can depend on T and X, but as a function of U, it looks like this. So it vanishes at U equals 0 and U equals 1. And then it has the property that the reaction, the graph of the reaction lies below the tangent at 0, at U equals 0. So if you draw the tangent here, the graph is below. Okay, so what does this mean? And of course, it also is positive between 0 and 1. It only vanishes at 0 and at 1. So what does this mean? Well, if you look at the PDE here, then this nonlinear term, you can write it as f over u times u. And then f over u would be sort of a linear coefficient in front of u, which of course is not, which depends on u itself. But anyway, so it would be like the coefficient in front of u. And then if you look at the KPP, the fu over u is greatest at u equals 0. Okay, so that means you can think of the fu over u as being the reaction strength. That's the essentially the exponential rate of growth if there was no space in here, if this was just a function of, if u was just a function of time. So there will be no diffusion, obviously, if this was just an ODE in time. And so fu over u would be then the strength of the reaction, and that's the largest at u equals 0. Okay, so that's the main property to have in mind for KPP reactions, that essentially the dynamic should be determined by the strongest, by the point 0 where the reaction is strongest. This is very different from different other types of reaction, for example, ignition, where the reaction is 0 up to a certain point, which may depend on time and x. And there's also an omega here because I'm talking about random reactions. So the reaction will also depend on some kind of random parameter. And so it would be 0 up to some point, and then it will be positive up and then all the way up to 1. Okay, so you can think of, for example, burning, right? So for temperature up to certain critical ignition temperature, nothing is happening. Then once you reach the ignition temperature, then burning starts happening. Okay, so these are actually very different. And I will be talking about the KPP case. I'll mention a little bit about ignition case later in the talk. And so in both cases and also other cases, except when this reaction is allowed to take negative values and it's sort of balanced between positive and negative, then things may be a little different. But in these cases of invading reactions where one equilibrium, let's say u equal 1, is stronger or more stable than the other, then we have a ballistic or linear growth of the region where the solution is close to 1. If, let's say, initially the region is bounded. And of course, there is a caveat. It depends sometimes. If the initial condition is too small, then, for example, for ignition reaction, it might just simply, the reaction might be quenched. So no reaction might be happening. Just very quickly diffusion would bring things to 0. And also, if advection were to be too large, there might be issues too, because the advection might, for example, blow off the region, the burning region. It might blow it off somewhere to infinity. Not infinite time, but infinite time. So it might be blowing it off away, or it might even disperse it. So under reasonable assumptions on smallness of the advection, this is the case, that the region grows roughly linearly. And you can see this in the simplest version of this problem, which is the 1D case. So there is only one spatial dimension. Reaction is independent of space and time. So this is the simplest version of the reaction-diffusion equation. And the first ones to look at were Kolmogorov, Petrovsky, Piskunov, also Fischer. Actually, I forgot to write down here in, again, one dimension. And what happens in there is that you have two front-like interfaces that form and move to the left and to the right. And they move at a constant speed, c star, some constant speed. Okay, so basically what you are seeing after a long time is that your solution is roughly the characteristic function of an interval that grows linearly in time. And the transition from values close to 1 to values close to 0 happens on a short interval in time that doesn't grow with t. Okay, so this just increases linearly. Okay, and by the way, this happens even if your initial condition is quite flat. Even if you make your initial condition very flat, the transition takes long space to go from 1 to 0. Very quickly, the solution develops this interface, which will be sharp, relatively sharp. Okay, so that's a feature of reaction-diffusion equations. Okay, so what that means now, this ballistic growth, is that if we want to look at some kind of homogenization, we want to look at large scale, large time behavior, we need to scale the same way in space and time. Okay, so we use the Balistic scaling here, and this is the scaling. So U epsilon is just our solution to the original problem, but scaled in space and time by epsilon. Okay, and then it solves the corresponding PDE. It's not important to read carefully this PDE. It's basically just you take the original PDE, you scale everything, the coefficient, the reaction in space and time by epsilon. Okay, but the point is that you want to look at homogenization on large scales. So you take this large scale PDE here, and then you say, well, let's for every epsilon make the initial condition to be in some sense approximately a characteristic function of some set. Now, why characteristic function of some set? Because of this sharp transition between regions where the solution is 1 and 0, at least in one dimension or in the homogeneous situation, but it turns out it's similar in the more complicated situation. And so if we are now on large scale, the narrow transition will become essentially just a jump. So it makes sense to look at initial conditions that approximate the characteristic function. Actually, they don't even have to, in the limit, be the characteristic function. They can be maybe 1/2 times characteristic function, something like that, but that's not too important here. So that's why I'm just writing approximately here. And so we want that. And so when you pick a small epsilon, what that means is that you start with initial condition, which is essentially 1 on a set G, and the variations in the environment happen on scale epsilon. So that means they happen on a much smaller scale than what you are looking at. Okay, and so that's precisely the homogenization setting you want to look at. So you want to think of what happens if we look at spatial and temporal scales, which are much larger than the variation of the random environment. And so then, if we have these solutions U epsilon, homogenization essentially means that we would like to, or in this case, for these reactions, reaction-diffusion equations, that the corresponding solutions should converge as epsilon goes to 0 to a characteristic function of some space-time set, which is essentially the evolution you get if you start with this space G in space, and then you let this process evolve, and that set G will spread and get bigger as the burning region is invading the originally unburned region, and so it will spread into that set, and that invasion is happening, or where the invasion is happening, that's precisely this set theta G, which is a space-time region. Okay, so that's basically where the if you basically take the time slice at time t of this set, then you will see where the invasion has spread by that time t. Okay, so what this means is that at least you should expect the homogenized dynamic to be essentially set evolution for reaction diffusion equations. Okay, and obviously, if it's a set evolution on a large scale and there is some averaging of the small scale randomness, then obviously there should be no randomness left in that homogenization limit. I mean, that's the whole point. And the evolution should be happening in a sense that the speeds of this evolution should be really depending only on the local look of this this set. Okay, so you very quickly find out that essentially the speed of propagation of this burned set should only depend on its boundary and its direction of this boundary and the normal vector to the boundary locally. Okay, so for example, if you have this kind of forest fire, this area is burned here, this area is not yet burned, then if the forest is essentially isotropic, so it really doesn't matter whether you turn left, right, or 20 degrees, you sort of see the same thing, then of course in every direction the fire should be spreading the same way. But if it's not, for example, it's on a slope and it goes upslope faster than downslope, then it will be direction dependent, right? But it should only depend on the direction in which the fire is spreading, how quickly the fire is spreading, if there are no other, in sort of larger scale inhomogeneities present. And so you can see, for example, here that if the fire is spreading, then on a large scale, it really has very little variation, the position of the boundary. And so basically it should be just spreading with the velocity depending on the normal vector. But of course, on a small scale, the boundary can vary a lot, obviously, because we have these small scale inhomogeneities. And you know, that's natural. But once you look at the large scale, you don't see these variations. And so here's the here's what it would look like if you start it from a initially small flame and let it just spread. And this is in the original scale, right? So obviously, this is the region where the solution is close to 1. And this boundary here is the transition between that and the region where it's close to 0. And so it will have some kind of, the boundary will have some kind of undulations. And then as time progresses, it will have those, and they will actually grow. But if you wait for a long time, you could hope for the growth of the undulations to be slower or less than linear, which is the growth of the size of this region. So the region grows linearly in time. So if you wait for a long, long time, and this of course would be much, much bigger than what the scale here implies, you would just see some kind of shape, or you could hope to see some kind of shape that just grows linearly in time, because these undulations will be very large, but much, much smaller than the size of the shape, because they will be sublinear. The size of the shape will grow linearly. And so this shape is a Wulff shape. It's called a Wulff shape. The name comes from crystal growth models, which also have this Wulff shape developing over time, over a long time, right? And so that's what you should hope if you start from an initially small region. Okay, so in the limit, you would have this Wulff shape. More generally, if you want to know what the homogenized dynamic looks like when you don't start just from an initially small region, then as I mentioned earlier, you should expect, or you should hope for, a solution so now this is after the scaling, after taking epsilon to 0, right? So there are two scales here. One scale is the original scale, where you can see this undulation, and the second scale is the homogenized scale, where you don't see those undulations anymore, and you don't have any space and time dependence here anymore, because that's the homogenized dynamic. And so in the general homogenized dynamic is such that basically this is the equation that tells you if you have a solution that is a characteristic function of a set, so it's a discontinuous solution of this first order PDE, then this C star is the speed in which by which a boundary at any point moves, boundary of that region where the solution is equal to 1, moves if its normal vector at that point is inside here. So this is just the normal outer normal vector at that point. Okay, of course, you know, gradient of u you have to understand in a sort of weak sense when the solution has a jump. But of course, this equation has also nice continuous solutions, right? So the solution, which is a discontinuous characteristic function of some set, is a discontinuous viscosity solution to this PD. Okay, so this is basically the normal velocity you should hope to recover. And then what does it have to do with this Wulff shape? So you could think of this Wulff shape as, well, if it's really growing, then in any direction, let's say this is direction E, it has some speed of growth. And that's precisely, if this is the Wulff shape itself, and then at a later time t, of course, it will grow to t time s. Now, this is in the homogenized scale, right? So then the velocity in time in which it is growing in this direction E is the length of this vector. So I call it S star E. But the velocity, it grows in that direction if a boundary has that normal vector, may be different, and in fact frequently is. It is the same if we are in the isotropic situation, when in every direction the medium looks the same, because then the Wulff shape is just the ball. And then the S star and C star will coincide. But in more general case, for example, this part of the boundary has normal vector E. And if you just look at it, if this Wulff shape grows as t times s, so linearly, little t times s, then actually the speed with which this part of the boundary grows in this direction or moves in this direction is actually this length. And so that should be the C star, but in fact, the C star may be even more, because it could happen that if we had really a flat half plane here, So this would be 1 here, and then 0 would be here, then the speed might be faster. This is not too important for the rest of the talk, but it's an interesting fact that I want to mention. And that could happen if we had a corner here. So now here, this Wulff shape is nicely round here. But if the Wulff shape had a corner, if it was like that, then we couldn't say that somehow the Wulff shape approximates the half plane. And then it could actually be, and this really can happen. There are examples of that when the front speed, so-called front speed, is faster than this length here. And so that makes things more difficult. The reason why I'm talking about, just to show you that actually the Wulff shape doesn't determine the homogenized dynamic in general. Okay, so there are examples when it doesn't, when these speed c stars are faster than this thing. So basically you get this by taking the vector E and dot it with any point in the Wulff shape and then take the supremum of that. And so the front speed might actually be faster than that. Anyway, but in the case of the Wulff shape, at least if we have the Wulff shape, which is spreading from a essentially single point or small region, then this should be a very easy dynamic, and which is this, right? So we start with G, which is the initial spatial set, which is essentially just 1 point. And then the theta G, the space-time set to which it spreads, will be union over all times. And at each time, you take that time cross T times S. Okay, and so again, this is in the homogenized scale. So this is sort of scale in which the inhomogeneities, the randomness happens on scales which are infinitesimally small. But of course, again, you can see this if you just start with the initial condition and you just let it spread and spread and spread. And after a very long time, you see this shape, or you hope to see this shape growing linearly in time with infinitesimally small undulations on the boundary. Okay, so I spoke a long time about this, but I hope this clarifies the ideas here. So let me now go to some specifics about KPP reactions. So one thing about KPP reactions, which you notice if you read a bunch of papers, is that anytime you see a result about spreading and spreading speeds, the spreading speed only depends on the reaction through the derivative of the reaction at u equals 0. Okay, so this is clear, for example, in the homogeneous situation I talked about, Kolmogorov, Petrovsky, Piskunov, where the C star speed, the speed with which these fronts are moving, is just 2 times square root of f prime at 0. So the prime is just derivative here at 0. Okay, and this is different, of course, from ignition reaction, where the speed depends on the reaction everywhere. But for KPP, it's different, okay? So it depends only on the reaction at u equals 0. And so that's because KPP dynamics is pulled. I already explained about this reaction rate here. And so there has not been no formal result expressing this property. And so I will tell you later about the result like that. So it turns out this can be formalized. And so before I do that, let me just talk about some standing hypotheses here. So our matrix A, which is the second order diffusion matrix, will be symmetric elliptic matrix, basically with some ellipticity constant lambda. I mentioned to you that we will need some bounds on the advection. So the bound will be this, where this lambda is that lambda here, and the infimum here is of the derivative of f with respect to u at u equals to 0. So essentially the infimum of the strength of the reaction over all space and time. Okay, and finally, we also need some kind of uniformity. So there is some GU. Basically, this just says that at every point between 0 and 1, the reaction cannot get arbitrarily small if we vary space and time. And it also says that it achieves, if you take fu over u, it converges to f derivative with respect to u at 0. It converges uniformly in space and time, and also in the randomness in the omega parameter as u converges to 0. So basically, just so that we need some kind of uniformity, obviously, and this is it. Okay, and then the last thing I want is something that will help me express this idea that the reaction, the speed of the propagation of the reaction depends only on the derivative of u at 0. And so is this, that if I have any reaction f as a function of u for any t and x and omega, then let's call a new reaction. I will call that f prime, but now this prime is not a derivative, it's just a notation. A reaction that I get by just taking the derivative at u equal to 0 and then just building this roof. Okay, so basically it's linearizing it, but I need this roof here because I have to have f prime vanishing at u equal 1. So I can't just take the linear reaction here. So I'll take this roof instead. Basically, it's the linearization. Okay, so that's the setup. And so here's a theorem that expresses this and also proves homogenization in the case of time periodic media. So we have time periodic and spatially stationary ergodic reaction and diffusion operator. And then this PDE under the above hypothesis indeed has a Wulff shape S, meaning if we start from a compactly supported initial condition after a very long time, we will see the region where the solution is close to 1 to be essentially time times the Wulff shape, and the rest, on the rest of the domain, d-dimensional domain, the solution will be close to 0. And indeed, if more generally, and this Wulff shape is the same for f, and if we replace the dynamic f in the dynamic equation by the reaction f prime, okay? So it's the same. And also in both cases, the homogenized dynamic, if we start now from some set G, which is of course now much larger than the scale of the randomness, then the set will be spreading with so there will be homogenization, but it will be a very simple type of homogenization where we take the following. We take any point in the set G, let's say this point here. So my set G is this inside here. Okay, we'll take any point inside a set G and sort of bloom a Wulff shape out of that point. So spread that point with a Wulff shape after time t, and do it with all the points in set G, and then take all those Wulff shapes, take a union, and that's going to be the set to which the region where solution is close to 1 spreads after time t. Okay, of course, this is in the homogenized scale. So if you go back to the original scale, it will be time t divided by epsilon. So a very long time, when epsilon is the scale of the inhomogeneities. Okay, so basically what you are saying here is that if your randomness has scale epsilon, then so much smaller than the scale you are looking at, then basically the solution is just spreading with this very simple geometric picture. So you take the initial set and you just bloom a Wulff shape at every point and take the union of those, and that's where the solution will be 1 after time t, or rather t over epsilon in the original scale. So after a long time relative to the size of the randomness, the very size of the scale of the randomness. Okay, and so that's the idea. And in fact, this convergence of these solutions to the characteristic function of this space-time set is locally uniform everywhere except of the boundary of the set. Because obviously on the boundary of the set, in the original scale, you have a sharp transition between values 1 and values 0. So on the boundary, you cannot have uniform convergence, but away from the boundary, you have local uniform convergence, which is to 1 inside this set theta G and to 0 outside. Okay, and this is for almost every omega. So this is the best result you could hope for. For almost every omega, you have this convergence. And the homogenization formula essentially is very explicit. Okay, so a few remarks about this. So I already mentioned this, that so we have the explicit and very simple homogenized dynamic. We also have this property that the front speeds actually are given by the Wulff shape. So this is essentially the same that if we are looking here, the front speed here, so how fast will a flat region with normal vector on the boundary, flat region on the boundary with normal vector E, how fast will it be propagating? It propagates with this speed c star, which is equal to this length. Okay, so the Wulff shape actually does define the homogenized dynamic. And this is, as I mentioned, not always true. In fact, there are examples of ignition reactions, even just periodic ones in 2 dimensions, and time independent. Okay, so these are here I'm talking about time periodic, but when I say periodic ignition, I mean spatially periodic and time independent ignitions where this is not the case. Okay, so this doesn't need to happen for non-KPP, but it happens for KPP, at least in this situation that I described here, and actually also others, as you will see soon. And so that's a very nice thing, because it gives me this very simple geometric formula for homogenization, rather than having to solve this equation, which is more implicit, obviously. And of course, we talk about viscosity, discontinuous viscosity solutions of that equation. Okay, so also it shows that the dependence on F of this homogenized dynamic is only through the derivative at u equals 0. Okay, so because remember, the Wulff shape, which defines everything, the homogenized dynamic, is the same for F and F prime, and F prime only shares with F the derivative at 0. Okay, so you can think of F prime as being sort of a template reaction with a given derivative at u equals 0. Okay, and all the others which share that derivative at u equals 0 have the same homogenized dynamic. Okay, so that's this formal expression of the idea that the dynamic only depends, at least in a leading order, only depends on the derivative of F at u equals 0. Okay, so a few remarks about previous results. I will only talk about those in multiple dimensions, because in 1 dimension, things are much easier. You don't have any geometry of the boundary of the region where the solution is close to 1. That region is essentially just an interval. Okay, so these results are all in the time independent case. So there is no time dependence in the coefficients or in the reaction. So there is a theorem stated by Lyons and Souganidis, which is essentially similar to this, but there is no time dependence, as I said, and it's not this explicit expression of the homogenized dynamic. Is the implicit one where the solution, the homogeneous dynamic is given by solution that solves a problem like this. So there is not the connection to the Wulff shape, but also it's stated without a proof. It's they basically just say that it can be proved using results from several papers, but the proof is not so simple for sure. And it's a different approach. It basically transforms the equation into a Hamilton-Jacobi equation, a viscous Hamilton-Jacobi equation, and then studies that. They study that. That's the main thing they study in that paper. So there are some more recent results where homogenization was proved. So for stationary ergodic ignition reactions, again time independent, up to dimension 3 by myself and Lin, if they are isotropic. And in fact, more generally, we can prove this homogenization when the Wulff shape doesn't have corners. Remember what I told you here about the Wulff shape. If it doesn't have corners, then hopefully you should be able to recover the front speeds from the spreading speeds of the Wulff shape. And indeed, we formalized this idea in this paper. So we have a proof like that. And in particular, if the environment is isotropic, then the Wulff shape is a ball, and then indeed it doesn't have any corners. But we cannot tell you when the Wulff shape doesn't have corners in general, and that's actually a very interesting question. Anyway, so that, and then again, speaking about stationary ergodic, without having to assume isotropic, we proved with Paul Zhang that indeed homogenization happens if the reaction has finite spatial ranges of dependence, meaning if two points in space are far enough, then the reaction at the 2 is completely independent as far as the randomness is concerned. So of course not spatially periodic, so it's, you can think of spatially IID. So in that case we can prove it, and we don't then prove that the whole Wulff shape doesn't have corners, but we prove that there exist front speeds, and then that using then some result from my paper with Jessica, that gives homogenization. Okay, so that's for stationary ergodic reactions and ignition ones in this case. And then for space periodic reactions, there were results by Alpha or Giletti for monostable reactions. They prove homogenization. And with Jessica, we can prove homogenization for space periodic ignition, even in dimensions greater than 3. So here, this is limited to dimension less than equal 3. There is a very interesting reason why there is the limit, but I won't have any time to discuss that. And there were some earlier results by Gertner, Freidlin, and Shin, Balistic, Hamel, Weinberger, but not homogenization results, but just existence of Wulff shapes and existence of front speeds, or both, but not homogenization. And I should mention that all these results, except of so all these homogenization results, so mine with Lin and with Zhang and Alford Giletti, not the Li and Suganis, they involve only the standard diffusion, no advection. Okay, so that's the remarks. Now let me get to a second result. So this first result was mine from last month, and then second result is with Paul Zhang. And so this is now in a non-time periodic medium, but rather time stochastic medium, so random in time, which was a difficult problem, mainly because we didn't have an important ingredient in the proof, which I'll tell you in the next slide. So now this will be a little bit more complicated here, because we need to have some kind of limit on dependence in time of the medium. So if we look at two different points in time that are far away, the medium should sort of be independent. Well, independent is the best, but you know, it turns out we actually don't need completely independent, but we need some kind of decay independence. So let's take H to be just the A, B, and F. I don't need any even F, I just need derivative at U equals 0. So let's take this, and then we'll need to define some filtration. So filtrations are sigma algebras, but are families of sigma algebras that are nested. And so basically what I want to do, I want to take, let's take FT plus. So that will be a sigma algebra in the, remember, everything is random. So the reaction is random. So we have some kind of probability space from which the omega comes. So probability space capital omega, F and P, and F is the sigma algebra. And so we define some smaller sigma algebras, which, let's say FT plus will be the sigma algebra we get when we take this environment up to time t, from time t to infinity, and just define the sigma algebra that we can get out of that, that's generated by that environment from time t to infinity. And FT minus is the same, but from time minus infinity to t. Okay, and so basically what we want is that FT minus and FT plus S plus are sort of independent or close to independent if S is large, right? So that's here. So you take any event from FT minus, and you take any event from FT plus S plus, okay, and you look at the probability of the event from FT plus S plus and its probability given the event from the FT minus happens, so the conditional probability. And you want to assume now, if these two sigma algebras were independent, so then the difference of this would be, of course, 0, right? But it turns out we don't need 0, we just need something that goes to 0 as S goes to infinity. So you just take the supremum of this difference and call it phi S, and then we'll need to assume that this goes to 0 as S goes to infinity. Okay, and so of course, if it's 0, then H has temporal range of dependence less than S. Okay, and so here's the theorem. So we take the above hypotheses, we take H to be the whole environment essentially. We assume it to be space-time stationary. So space-time stationary just means that if you look at any point in space and time, the law of the environment is the same. Okay, so meaning you are equally likely to get some environment in one space and time, point space in time, and in another point in space-time. Okay, that's the same environment you are equally likely to get. Okay, so that's stationarity. That's absolutely necessary for proving almost anything, right? And so if we can show that phi S converges to 0 algebraically, so for some alpha greater than 0, S to alpha phi S converges to 0, then the previous result holds, meaning we get the Wulff shape, we get homogenization. The Wulff shape only depends on the derivative of F at U equals 0, and the homogenization is precisely this blooming of the Wulff shape at all points of the initial set. Okay, so this explicit result. Okay, so we get that, and that holds for almost all omega. so which is the best result you can hope for. If we only get phi s converging to 0, but we don't have an algebraic rate, then we can still prove this, but the homogenization happens in probability. And what that essentially means that you can't just first fix an omega, which is one of almost all omega, and then you just take the scale to infinity, meaning epsilon to 0. But you first take epsilon to 0, and then for every epsilon, you have a large set, and the larger epsilon is larger and larger set of omega for which everything is good. But as you converge with epsilon to 0, that set of omega might not just be growing, it might be sort of jiggling around, become bigger and bigger in probability, but you can't guarantee that there will be a full measure of omega, which sort of eventually all are in that set. Okay, so that there is a small difference between those two. And so in this case, we can only prove convergence in probability. Okay, and well, but in any case, these are first results in general space-time dependent media of this type. So both actually, this result is really the first one in space, time periodic, and then more general time dependence. This is the first result in that case. Okay, so I don't know, how much time do I have? Not much, right?
Hi, maybe 10, 15 minutes.
Okay. Okay.
Yes.
So let me maybe skip these next two slides and I'll see whether I'll have time to come back to it later. It's basically just saying that the same results I'm talking about here also apply to so-called G equations, which is a different model of flame propagation. It's a first order model where we don't get the propagation out of interaction of the reaction and the diffusion, but we already sort of bake it in. And so the propagation speed is c, which is isotropic. It's in every direction the same, but of course it depends on space and time. But locally, it's the same in every direction. And then there is some kind of advection, which moves around in some kind of fluid medium. This burning or whatever burning substance, right? And so the G equation is has a convex Hamiltonian but not coercive, and that makes things difficult. And so there was very little work when it comes to time dependent reactions, time dependent environments in this case. And so it turns out our approach works for this as well. And so in particular, this result with Zhang extends a previous result of Burago, Ivanov, and Novikov, who proved homogenization for this G equation when the medium is space-time stationary again, as in this result, and has finite temporal range of dependence. And so we can actually extend it to a more general dependence in time, as long as this phi s converges to 0, either just plainly or with some algebraic rate. Then again, these results extend and homogenization holds in that case. But I will not go further into it. Yeah, that's good enough. So let me go back to reaction diffusion equations. Let me tell you in the last 10 minutes a little bit about the proof, which in both these cases, so in the time periodic case and the time more general time stochastic case, consists of two main steps. And so the first step is to prove that a Wulff shape exists. And then the second step is to show that the homogenized dynamic exists and is given by this blooming of the Wulff shape from every point of the initial set G, where initially the solution is close to 1 in the homogenized scale. Okay, so let me first talk on this slide about the first part of it, the Wulff shape, existence of Wulff shape. So we just start from 0 essentially, and then bloom or grow out of there. Okay, and so this is all in the original scale. Okay, so we have randomness on this scale, and then we are asking what happens if we grow to a very, very large region. So we'd like to see a very, very large Wulff shape for large times. Okay, and so this actually there is a nice tool in the probability theory, which is Kingman's subadditive ergodic theorem, which can be used to prove existence of this Wulff shape. And so here is how you use it in PDE. So you start, you have your PDE, and you start at any point y with a given initial value, which is just some kind of bump function. Let's say it's greater than 0, obviously, let's say it's less than 1/2, so some kind of bump, compactly supported bump. Okay, and then ask, how long does it take before this bump spreads from this point y to a different point z? And so I will say that the time is such that once the solution starting at point y covers the bump centered at z, so move to z, that's the time it takes to spread from y to z, or to travel from y to z. Okay, so I will call it tyz, which of course depends on omega, on the randomness. Okay, and so let's just assume, let's talk about the case when everything is time periodic, the environment is time periodic. Let's say the period is 1, so we can talk about integers. So let's take the time to be the smallest integer time, because it's easier to do it, to have the same, starting at the same point in the period, in time period. So the first integer time, and now we are asking how fast do we move in a particular direction? And so we want to know how fast we move from 0 to n times e, where e is the vector in the direction, the unit vector in the direction, right? And so if we want to have homogenization, we should have a limit of that time divided by n as n goes to infinity. If we get that limit, then 1 over that limit is going to be the speed of spreading in that direction. Okay, so that's the goal. And so for that, there is the subadditive ergodic theorem, and subadditivity holds here. It's the main condition, because the following is true. If we go from any point to any different point, the time it takes is no more than going from the first point to some intermediate point, and then that plus the time it takes to go from that intermediate point to the second point. Okay, that's obvious, and that's the subadditivity hypothesis here, which therefore holds. And then Kingman's subadditive ergodic theorem is just a black box that spits out, yes, this limit does exist. Okay, if the environment is stationary ergodic. Now you need to work a little bit to justify the hypothesis of Kingman's theorem, but after that it's just a black box. And so you get, indeed, almost surely this limit exists, and the 1 over that is the speed. And then you can show with a little bit more work that essentially that limit is attained uniformly in all directions in space. Okay, that takes a little bit of work, is not too difficult. And therefore you get actually that for almost every omega, you converge to a Wulff shape, meaning that if you start from point 0 and you spread, so for some kind of compactly supported initial condition near 0, and you spread after a very long time, you will essentially see t, that's the time, times s, where s is the Wulff shape, and that's where the solution will be close to 1, and outside of that region it will be close to 0. The transition between those two regions may be very large, but it will be sublinear in time. Okay, so if you scale everything, you will just see a characteristic function of t times s, or characteristic function of s, depending on how you scale. Okay, so that's how you prove the Wulff shape. Now, if you are in time dependent situation, general, not just time periodic, you can't use Kingman's theorem. And so we were thinking about this with Paul Zhang for a bit, and then we realized we just need to prove our own time dependent, non-autonomous subadditive ergodic theorem. And so we did that. And so here's the theorem, and it's a little bit complicated, but basically what it says is you take your filtrations, which are essentially in the PDE setting, they are the ones I talked about before. It's the environment, so ft minus is the environment up to time t, and ft plus is environment from time t to infinity. So the filtration, the sigma algebra defined by that, right? And they are ordered like this, obviously, which was the case before as well. And so then you take the time it takes to travel from m to n. Think of me, ne, but this is just a purely probabilistic result. So there is just m and n, and the time is bounded. But this is a time when you start the travel at some time little t. Okay, and then the subadditivity hypothesis should be something like this, where if you go from m to n starting at time little t, that should be less than equal going m to an intermediate point starting at that time t, plus time going from the intermediate point to n, but starting at a later time, which is the time where you arrive at the intermediate point. So it's t plus this previous time. Okay, and so that makes things more complicated. And then there are some kind of standard things about essentially space-time stationarity. So distribution of this thing is independent of time and m. And then this measurability, obviously, that's we talked about that. That when you start at time t, then this random variable should only depend on the environment starting from time t to infinity. So it's ft plus measurable, and there is something similar with ft minus. I really don't have much time to talk about. And then we have this hypothesis that this phi s, which remember depends on these sigma algebras. So it was defined here. Okay, so this same phi s needs to converge to 0 algebraically. And then there is one more hypothesis which says that if you start from time t traveling from m to n, that will take no longer than if you start at a later time and add to it the time you waited before you start. And in fact, this is only necessary for s greater than some constant. Okay, so, and there is a good reason for that, but again, I don't have much time to spend. So this is not necessarily a natural condition from the probabilistic point of view, but it's very natural from the PDE, okay, point of view. But even from the probabilistic, depends on how you look at it. Anyway, so it turns out that we still have this result. So there is an almost sure limit of T0n over n, and therefore we actually can use this in place of Kingman's theorem to conclude the existence of a Wulff shape, even in this time-dependent case. And we also have a result in probability when this phi s only converges to 0 plainly. Okay, so I won't have time, and also I wouldn't want to talk because the proof is completely probabilistic. There is nothing to see as far as PDEs are concerned. So I see I only have a couple of minutes. So very quickly about the second step, which is how you go from the Wulff shape to the full homogenization, to this homogenization being just this blooming of Wulff shapes at every initial point of the initial set. And basically what that requires is first to show that this blooming towards a Wulff shape is sort of uniform with respect to OT perturbations of the starting point. So not only you reach the Wulff shape and you start from 0, but also if you start from a point that is 15 times t away from 0, then after time t, you also reach the Wulff shape, or rather t times Wulff shape from that point at the same rate essentially as from the initial point O, origin, from the origin. Okay, so essentially, so this is what it means, that if y is within some lambda t of the origin, then you reach the Wulff shape after time t, you reach the Wulff shape y plus ts from the point y as well. Okay, so it can be done. It uses Wiener's ergodic theorem. And then there is a new result, which I also wrote a couple months ago, last month. So, and it's a result which expresses this idea of why everything for KPP reaction diffusions depends, as far as speeds of spreading are concerned, depends only on the derivative at u equals 0. Okay, and so I call this the virtual linearity of the PDE, and it's the following. So we have again the standard hypotheses, and then there is a function converging to 0, and for every delta there is a number such that the following holds. You take a solution of your equation. Now there is no need for omega, by the way. This is just deterministic. And then chop up its initial condition into little cubes. So chop it up into cubes and make it 0 outside of the cube. Okay, so that initial condition you use un prime. And then you solve the same equation with these chopped up initial conditions, but also you can replace your reaction f by this f prime, which shares with f, which is the template, which shares with f only the derivative at u equal 0. Okay, so you chop up your initial condition and solve the equation with a different reaction with f prime. Okay, and then there is this comparison that u is essentially just the supremum of these solutions over n. So there is some error which goes to 0, and there is some shift in time. There is minus delta t, and here you can put plus delta t or even t to delta, even that works. But the point is, up to these shifts, so in a leading order, the solution is equal to the supremum of these chopped up solutions or solutions with chopped up initial conditions. And so why do I call this virtual linearity? Because first, it tells me the dynamic up to leading order or in leading order rather depends on the derivative of the reaction at u equals 0. But also it tells me that if I split the initial condition into smaller bits of it and then solve and then add up, essentially that gives me the solution of the original PDE with the original initial condition in the leading order. And this is a special property of KPPF, and you can't hope it to hold in general. But this is essentially the result that formalizes that dependence on only the derivative of reaction at u equals 0. Okay, and so it turns out the proof is not too difficult if you want to get just something. It's a little bit more involved if you want to get a sharp bound on the velocity. Remember, there was a bound on the velocity for which this holds, so that it doesn't blow off everything to infinity, for example. And so with the sharp bound, it's a little bit more difficult. But I can see that I have to end. So I will not. Maybe if somebody has a question, I can talk about it. But let me just not talk about it. So I'll stop here. Thank you.
Well, thank you very much. If you want to continue for a minute, that's okay.
Okay.
Well, yeah,
I can if that's fine.
yes.
I can just say really quickly here. So so first, let's do just a simple case when f is equal to f prime. Then things are a little bit simpler, and f prime is concave. And if you use concavity, you can actually show this thing very easily. So what is here? So the first inequality here is obvious because un prime has initial condition less than u, and we have comparison principle, and of course they solve the same PDE because f is equal to f prime, right? So this is trivial. And this, well, u is less than 1 always, so that's fine. But u is also less than the sum of these guys. You can just find it very quickly if your reaction is concave. Okay, so if these solve the same PDE, if the reaction is concave, then you get the sum solution for the sum of initial conditions is below the sum of the solutions. But then you have a sum here, right? So how do you turn that into the supremum? Okay, and the point is that the number of n's which contribute to this sum is essentially just algebraic in time, in t. So by any time, the number of the solutions that really contribute to this sum, the other ones are very, very small. They're exponentially decaying as n goes away from x. So the number of those that contribute is linear in t to power d. Okay, and that is because of this finite speed of propagation of solutions and something called exponential hair trigger effect. So if you have even a very, very small value at some point, because we have KPP reactions, that will grow exponentially very quickly. And so you cannot have, you know, not too small value very far away, because that would just very quickly grow, and that would make the propagation to be very fast, which of course doesn't happen. So I have to be a little bit quick here, but that's the idea. So then you can show that essentially at least one of these that contributes must be no less than the solution u divided by t to power d. Okay, but then that means if you wait for a little bit longer, and you can wait for delta t or even t to delta, that will grow exponentially and will grow above u. Except when u is very close to 1, then it might slow down, but then it will grow above u minus something small, little of t to 0, little of 1, basically. Okay, so that's the idea. And if you, of course, this is for f equal f prime. If f is not equal to f prime, you need to work much harder. You get extra errors, and that's where you get this transformation from t to t minus delta t inside this un prime, right? So that's where you need to get this. Okay, anyway, so that's the idea very quickly. Yeah, thank you.